All right, cool. Um, I hope everybody is not going to be sleepy through this. I have a very ambitious goal of doing 4 demos. Let's see how that goes. I hope that the demo gods are with me. My name is Abdel. If you don't know me, I work for Google. I'm based in Stockholm, and I do a podcast called Kubernetes Podcast by Google. By show of hands, how many people here listen to that podcast? Okay, the rest of you, I'll just give you a minute to subscribe. Just kidding. So I work on everything Kubernetes and service mesh and containers. But today we're going to be talking about fine-tuning and serving large language models on Kubernetes. Maybe this is the 10th or 100th time this year that you were in a talk in front of somebody talking about AI again. I assure you this is not an AI talk. I don't care really about AI. That's not actually what makes money, really. I'm just going to show you why Kubernetes, I'm going to try to answer the question of why Kubernetes is becoming big in the AI space and show you and demonstrate to you why people care about Kubernetes in the AI space. I'm just going to start with the number 9 out of the 10 biggest AI companies today use Kubernetes for both training, fine-tuning, and serving. And this is not new. It has been around for a very long time. Kubernetes itself have been doing a lot of, as the open source project, they have been doing a lot of efforts to make Kubernetes run AI workloads for a very long time. It's just since ChatGPT last year that have been kind of accelerated. So, what we're going to talk about today? Distributed machine learning training on the distributed machine learning Kubernetes, generally speaking. And when we say distributed machine learning, it means jobs running across multiple nodes on the same cluster or across multiple clusters. Today we're going to focus specifically on fine-tuning, but the same techniques applies to training. Running the model, so once you have the model trained or fine-tuned, how do you actually run it? So that's what we call inference. I'm going to touch on some open source tools that are becoming so popular in the open source space these days, and a little bit talking about what the future looks like. So what is fine-tuning? Fine-tuning is the act of adapting a pre-trained model to serve specific tasks. So an example is you take a large language model that is trained to do language, and then you train it on Japanese. So the model is already trained to recognize patterns like words, sentences, comma, spaces, etc., question mark, exclamation mark, all that stuff. And then you train it specifically to do a specific language, Japanese. So you don't start the training from scratch. You already take a model that knows how to speak, and then you just tweak it to speak a specific language. Typically, fine-tuning, like training, requires a huge computational power. And this computational power sometimes exceeds the possibility of running them on a single computer, which means you need to run them in a distributed fashion. So what is distribution? Well, distributed is essentially the answer to the question of why use one computer when you can use multiple ones, right? In the distributed compute space, Python is the primary language for a lot of these things. So we're going to be looking at a Python code today. And with GenAI and GenAI becoming a big deal in the tech space, distributed compute is no longer optional. It's actually a requirement. I can give you tons of examples of why you might need to do distributed computing for machine learning. But example number 1 is the fact that to do machine learning, whether it's fine-tuning or training, you need accelerators, so GPUs, TPUs. There is a physical limitation to how many actually GPUs you can attach to a single node, and that's typically the physical limitation is how many PCI Express ports are available on that specific node. And typically for most mainstream servers, it's 8. So if your model needs more than 8 GPUs, you don't have an option to run it on a single node. You need to run it on multiple nodes, right? So why distributed computing? Well, scalability, obviously, being able to scale across multiple nodes to be able to do multiple rounds of compute. If you try to fine-tune or train a model on a single node, that's going to take forever, especially if the model is big. Availability, being able to actually pick and choose which nodes and which configuration of GPUs or accelerators are available for you. Efficiency, running on multiple nodes is typically more efficient than running on a single node. Typically, fine-tuning or training is a factor of how much memory and how much GPU memory is available on the node rather than how much CPU. Training and fine-tuning are GPU and memory-heavy tasks. And flexibility, being able to choose to run on one specific type of hardware versus another. That also comes with challenges. The main challenge is consistency, right? So one of the main common techniques when you are doing training or fine-tuning of machine learning models is that you don't run the fine-tuning or the training as one single task. You usually run it in batch tasks, so in incremental tasks, and then you save the model between each round of compute, right? You snapshot the model typically. And so being able to snapshot the model across multiple nodes is a challenge. So you need some sort of like shared storage that all the nodes can talk to, so they can all snapshot whatever they are doing and then pick the last snapshot and then work on it, right? Fault tolerance is obviously a big one. Handling concurrency. I'm going to show you an example later how that typically works. Load balancing, so being able to, this is actually, if there is anything I would probably recommend you to go look after this, is the work that the Kubernetes project is doing in the load balancing space, because I'm going to spend 30 seconds explaining it very quickly. When you have to do load balancing on a typical backend application, you load balance based on requests, right? So you see how much requests are coming, and then you allocate the requests to the instances behind, and that's typically how your load balancer will load balance stuff, right? In the LLM space, that's not how it works, because what determines the load is not actually the amount of requests, but it's the amount of tokens or the size of the requests coming. Typically, how much text the user inputs toward the model. So in the open source community, they are actually working on something called the LLM gateway, which is based on the open source gateway API to be able to address load balancer for this specific kind of problems. And then there are security concerns. I'm gonna skip through this. And obviously, we shouldn't forget that the cap theorem is something that works always against us. The cap theorem is basically you cannot have all these three things. You can only have two out of them. You can have consistency, availability, or partition tolerance. You cannot have all of them at the same time. So with that in mind, let's look at a very simple example. What I did is I wrote some like very basic, I'm not the best developer around, even if my title is technically developer advocate, but I wrote some like Python code that basically uses the transformers library from Hugging Face to fine-tune a model. So I'm not going to bore you with the code, but essentially I start with the base model, which is the Gemma 2B model. Is it visible? Can you see it in the back? Good, perfect. And then my new I use this dataset called SQL Create Context. It's a dataset that contains questions and answers about SQL queries. And then my new fine-tuned model will be called Gemma 2B fine-tuned. Then I have a bunch of parameters. As you can see, all these parameters are actually environment variables. So if I'm running this inside Kubernetes, I can try multiple rounds of fine-tuning by changing the parameters. So I don't have to like rewrite my code. I don't think that this is something I need to teach you. And then somewhere here, I execute my fine-tuning. I'm not going to go too much into, like, I have to transform the dataset. That's not a problem. And typically, this is where the fine-tuning actually happen. Once I find it, this is pretty much it. So this is the actual fine-tuning task. So this will just use the library to fine-tune my model. And then once my model is fine-tuned, it will save it and then push it to Hugging Face. So what I did is I actually wrote also a Docker file to package this code. So I used the CUDA library, the CUDA base image with Ubuntu to be able to run on top of a GPU, install some dependencies, and then basically just run my fine-tuning model, right? My fine-tuning task, sorry. Then once I did this, I packaged all this container into an artifact registry, and then I wrote a job. So in the Kubernetes space, you have this API called job, which allows you to basically run a single job, and then there is an API called cron job that allows you to schedule jobs, right? And so my job has the container, which is this one, and then it uses 4 GPUs. These are all the arguments that you have seen, all the environment variables you have seen. It needs a Hugging Face secret because I need to push the model to my Hugging Face. And then I run it on a node that contains an NVIDIA L4 GPU. So I know that I am a little bit showing off right now because I work for a cloud provider, so I'm able to get GPUs. If you're not, don't feel bad about it. Everybody is not able to get GPUs these days. So I already actually executed my fine-tuning job, and it's completed. You can see the status is completed. It was successful. I was lucky. The job API inside Kubernetes is actually pretty good, but it's pretty limited in terms of what it can do. You have certain parameters in the job API where you can define your retry policy, like if the job fails, how many times do you want to retry it. But there is no way for the job API individually to be able to say, wait until resources are available and then run my job. So if I am dependent on some sort of auto-scaling where I can run my job and then expect the cluster to auto-scale to run my job on top of it, if the cluster doesn't have enough resources, because again, GPUs are not available, the job will just simply fail, right? In my case, it just succeeded. I can quickly inspect the logs if I want. Unable to retrieve logs. OK, the logs have disappeared for some reason. All right, OK, I don't have logs. But believe me, I did the fine-tuning. It actually ran. I can show you. This is my Hugging Face profile, and I can already see that I have the fine-tuned model there. It just pushed 3 hours ago because I just ran it 3 hours ago. And so now I have my fine-tuned job, like my fine-tuned model that have been fine-tuned using a job and then pushed back to Hugging Face. So go back to slides, and I'm going to show you later what I mean. Now, I'm going to quickly talk about this project called Q. You remember when I said that jobs have this challenge where you cannot really orchestrate them in a way that makes it possible to ensure that your job will for sure run? And if you try to run a job and there isn't enough resources, it will fail. Q is a project that we open source that tries to address this problem. So what Q does, it allows you to define what we call local queues. So a local queue is essentially a set of resources that you can allocate to run jobs. And it's meant to be able to allocate resources in the cluster in a fair way across multiple teams running jobs, and also have a priority between high priority jobs and low priority jobs. So it's sort of like an orchestrator for jobs on top of Kubernetes. It's Kubernetes agnostic. You can run it on any Kubernetes installation in any cloud. But basically, the way it works is that your users will still use the job API. They will push it to Kubernetes. Q will just ensure that those jobs will run to success whenever the resources are available. And if resources are not available for whatever reason, for example, all the GPUs that you have in your cluster are being used by a high priority job or a high priority task, then it will just pause that job until the resources are available, then run them. So if you have challenges making sure jobs run and you don't want to keep retrying until resources are available, make sure to check Q when you have time. The next tool I'm going to introduce is Ray. Ray is one of these most popular open source tools right now in the open source space for doing AI and ML workloads. It's actually a Python framework that is written to be able to act as an abstraction layer on top of compute platforms. It does run on Kubernetes, but you can also run it on virtual machines. So it's a Python-first approach. It has a simple API. It's designed to be scalable, and it supports CPU, TPU, and GPU. You can really divide Ray into 3 layers. There is Ray Core, which is the component that allows you to run your actual workloads. There are libraries for doing serving, tuning, training, data preparation, and reinforcement learning. So those are optional libraries. You don't have to use all of them. You can use 1 or 2 or none. And then you have the cloud part, which is where I sit. And that's essentially how do you actually run Ray once you have written code in Ray. So it's pretty interchangeable with existing libraries. So you don't really have to use the Ray libraries to do all of these tasks. You can use other libraries if you are familiar with them. Ray, because it's open source and it's flexible, it allows you to swap in components as you see fit. So let me show you an example very quick. And this is where we're going to see really what we mean by distributed. So I have already deployed Ray into my cluster. I'm going to show you real quick. I don't want to go into details of Ray. This is not the purpose of this talk, really, but I just wanted to show you. So I have a Ray cluster because Ray itself follows a worker node kind of control plane architecture. So it has a control plane, which we call the head. That's the first pod, the 2 pods I selected, that has head in it. And then the group worker, that's the actual worker node, which will execute the job. So these 2 components are running as pods inside my cluster, which means using Kubernetes, I can run Ray and I can scale up and down, or I can just create a Ray cluster, execute a job, and kill it as I see fit, right? Then once I have that running, I can basically inspect. There are 2 things I can do. I can look at the dashboard. So on port 8265, I have the Ray dashboard available. It gives you information about my cluster. So I see my cluster has 2 nodes. So one is the head node, and one is the actual worker node. It has jobs, so I can look at the jobs. I can see success, failure, logs, all that stuff. And then I have a bunch of other metrics. I'm not going to go too much into details. And then, so this is to be able to inspect the actual dashboard. Then it has a different port to be able to expose the API that I can actually use to run my workloads. So in the case of Ray, the API is exposed on this port. And so all I have to do if I'm running Python code to be able to do machine learning workloads is I have to initialize my Ray library and give it the port, the IP address and port of the head node, right? In that case, it's localhost 10001 because I am doing a port forward on my local computer. Then I have to, of course, I have to import Ray, which I already installed it. And in this particular example, I have just an array of words, right? I wrote a retriever function that retrieves functions or retrieve items from it gets an item as an input and retrieves it from the database or from the list. Then I print some runtime. I'm going to show you later what this means. And then I have two functions. One function will run the retrieve function sequentially, which means it will retrieve one item at a time. And then I have a parallel function, which references my retriever function, and then executes that in a parallel or a distributed fashion. So, and then I run them one after another. So I call the sequential library, the sequential function, and then the parallel function. Now, the only thing that makes this array job is the fact that it has an @array.remote. So if you have existing code and you want to run it on a remote array cluster, all you have to do is just decorate it with the @array.remote function, and it will instruct array to run that on a remote cluster instead of a local cluster. Obviously, you have to initialize with which remote cluster do you want to run on. So let's go ahead and run this one, and I'm going to show you exactly what I mean by parallel versus sequential. So I just run my Python library, calling the parallel.py. It's going to give me an error here about mismatch versions, but I don't care too much. And I can see here, running sequentially, retrieving data from the dataset, or, I mean, it's not a dataset, really. It's like just an array, but you can think about it as a dataset. Running them in a sequential function took 4.5 seconds. Running them in a parallel took 3.76 seconds. So in one case, I am just like retrieving one item at a time. And in another case, I am just like parallelizing that retrieve job. So you can think about, this is a very dumb example, but the thing you can think about is think about each of these items in your database as being a resource that you have to retrieve and do some processing on it. Like, for example, those are all files that you have to download and then do some calculation on them, and then store that calculation somewhere, right? So using parallelization, we can parallelize that task. And if my array cluster has more than one node, in my case, there is only one node, but it has like 2, 3, or 4, this will run much faster, right? So it should take less than 3 seconds to run my job in a parallel fashion. I can go back to my array cluster here and look at the jobs. I can see that the last job that I run is this one here. Let's try one thing. I still have a little bit of time. I'm rushing for no reason. Let's scale up my cluster. So this is one of the cool things about running actually array on top of Kubernetes, is being able to just take this cluster here that I run. I will edit it. And then I will find my replicas somewhere. And then I will turn that to 2. So this is in the worker group spec. So that's the spec that defines the amount of replicas or the amount of worker nodes I have. So if no, not 21. That's a little bit too much. And then if I do kubectl get pods, then that should bring up a new pod here. I hope it's not going to take as much time. Because I have ADHD, I'm going to do a watch to watch it doing its things. But anyway, I'm just trying to demonstrate that actually running stuff in parallel on top of Kubernetes can run things faster. So this is a very dumb example of like a single array with multiple objects that we're trying to retrieve in a sequential or in parallel fashion. But the example can be applied on machine learning tasks that need to run in parallel on a much larger scale. So my second worker node is already running. So now if I try to run that parallel function one more time, hopefully the parallel part will take less time, because I have more than one worker node. So let's see. Sequentially, still 4.5 seconds. Parallelly, 3.06 seconds. So it's 7 seconds less, no, 0.7 seconds less than the previous run, right? And then, of course, the more worker nodes I have, the less time it will take. So that's Ray. And so to give you an idea about why Ray is important and why it's becoming such a big hype, it's because pretty much like people building platforms for doing applications, people also are building platforms for doing machine learning. And Ray acts as that middle layer for your platform framework. You can think about it as backstage for machine learning, essentially, really, without a cool interface. But you can think about it as backstage. As long as it's available inside the cluster, a machine learning or a data scientist engineer can just use a notebook, which is what typically machine learning and data science engineers are used to basically run on top of Kubernetes. By the way, if you're curious, there is actually a way for you to run a multi-tenant Jupyter book or notebook on top of Kubernetes. If you are a platform engineer and you are serving multiple data scientists and multiple machine learning engineer, you can run a Jupyter book on the same cluster and then give each engineer their own notebook so they can do things with it. With GPUs, with TPUs, with whatever kind of accelerators they need. So Ray really runs as that middle we call machine learning platform layer that will bridge the gap between what data scientists, machine learning engineers are trying to do and where they run on. We have a reference architecture, if you're curious to look at it, that uses partially Ray. So this is a reference architecture that does data processing using Ray. It does fine-tuning using PyTorch, and then it runs the model using something called VLLM, which I'm going to look at in a second. I'm going to show you what VLLM means. It's essentially an inference server, an open source inference server. You can also choose to do all of that using Ray. So you can swap in components to be able to either use or utilize Ray for the entire lifecycle or utilize it only for one of the components or one of the steps. So why do we run this on Kubernetes? I hope I don't have to explain what Kubernetes is. Otherwise, you've been wasting your time in the last 1.5 days. But we run this on top of Kubernetes because Kubernetes gives us the infrastructure automation we need. Being able to spin up nodes with GPUs and TPUs is much faster to do on Kubernetes than doing it manually. The scalability, the high availability, the advanced device management, and the most important thing is the multi-cloud availabilities. Because Ray runs on raw, open source, upstream Kubernetes, wherever Kubernetes is available, you'll be able to run Ray on top of it. I'm going to skip through this. I'm going to cover the last parts with demos, and I think I will have time for questions if you have any questions. So now we have taken a machine learning model, Gemma 2. We have fine-tuned it on top of SQL dataset to be able to answer SQL questions, right? Then I showed you how you can do the same more or less with Ray, or running parallel distributed workloads with Ray. Now, the output model, which is the actual fine-tuned model that I have, once I have it, I need to run it, right? I need to execute it and be able to talk to it. And this is what we typically refer to as inference. Sometimes people also use the term serving. Serving or inference are pretty much the same thing. It just essentially means you have a model, you need to run it so you can invoke it. So there are multiple ways you could do that. There are 3 very famous open source tools today on the market. One is called VLLM. One is called TGI from Hugging Face, and then Ollama. You're probably familiar with Ollama. How many people here have used Ollama on their laptops before? OK. So Ollama is just a container to be able to run machine learning workloads. You can actually run Ollama on top of Kubernetes using the same exact container. Not the same binary you have on your laptop, but the same container that can run inside of Docker. You can also run it on Kubernetes and then download the model inside, and then Ollama will give you like an API endpoint that you can talk to. I'm going to show you today VLLM, which is one of those popular platforms. So it's just a VLLM. This is just a typical Kubernetes deployment. It runs the PyTorch VLLM inference server. And then it has like a bunch of like requests. One of them is being able to have a GPU. And then basically all I do is run the VLLM and then specify which model I want to run. In this particular case, I am specifying a model which is on Hugging Face. So VLLM will turn up, download the model from Hugging Face, and then give me an API endpoint. So once this is deployed, I also have a service here that does expose my VLLM deployments on port 8000. So all I have to do now is do a kubectl get services. I have my service here called LLM service, so I just do a port forward. Port forward on port 8000, and then spin up a new. So I have just an environment variable that has a user prompt asking the model question of what the total number of attendees with age 30 at KubeCon, and then giving it as a context a table that contains name, age, and which KubeCon, so which events. And then if I curl that, I should be able to get an answer with the right query, hopefully. Let's see. So this should be able to invoke my model and give me an answer, hopefully, if everything works well. Or not. All right. That's the joy of doing live demos, I guess. Let's try one more time. No. Let's do this. there we go. Now it works. I don't know what happened before. So the output or the answer is this one. So I got basically, actually, no, that's a wrong answer because I asked over 30 and the query has over 3. All right, never mind. It's an AI hallucinating. But you get the point. The point is I took a machine learning model, I trained it. No, actually, no. I know what's the problem. Can somebody tell me? Sorry? Yes. So I actually truncated the output explicitly. So I think I limited. Oh, now I got more than I needed. But at least I have the age over 30. So this is correct. So this is one of the challenges, because I told the model to not output more than 24 tokens. So it truncated the answer. But now I asked it to give me 248 tokens, so it just repeated itself multiple times. So see, this tells you how accurate those LLMs are. They are either wrong or too right. Anyway, so this is my model running using VLLM. So this is a very simple server. You can actually, VLLM does have a Prometheus port, so you could expose some Prometheus metrics if you need to autoscale it automatically. So you can just expose metrics and use your horizontal pod autoscaler, which I think everybody knows, to be able to autoscale your deployment. The last thing I'm going to show you real quick is you could do the same using Ray. So Ray has a library called RayServe, which I have here. And so all you do is define a Ray service. And I'm not going to go through all the details. It basically has to point to like a GitHub repository where your code is. You tell us which model you want to run. And then it actually still uses VLLM under the hood. And this is where you specify how much resources you want your cluster to have. Once you deploy this, what it will do actually is that it will actually deploy a Ray cluster for you, which is this one here. And once that Ray cluster is up and running and this model is serving, it will give you an endpoint, which is this one here. So all you have to do is the same way we did this port forward here. We can just do another port forward on that particular endpoint. It's already used. I have to kill it somewhere, I guess. Where is it? Yeah, here we go. And then I can do that. So that's running. Then I can just do the same query as earlier. And that should just give me the same answer, basically. So hopefully, yeah, anyway, again, wrong, but whatever, you get the point. So yeah, that's essentially the two ways you could use, you could serve a model. You could either use raw like basic containers like VLLM, TGI, whatever, Olama, or you could use Ray service. The last thing I'm going to leave you with is real quick, 2 big improvements coming to Kubernetes. One, something called dynamic resource allocation. So DRA is a feature in Kubernetes that was introduced in 1.31. I think it's still in alpha or beta stage, I don't remember. What it does, essentially, it allows you to define a policy based on GPU and TPU utilization, so that if a pod is utilizing, as in allocated, has a GPU or TPU allocated to it, but it's not using it, you could actually choose to unschedule that pod to schedule higher priority pods. The simple way you can think about it is, I think, is anybody familiar with the concept of balloon pods on Kubernetes? You never heard this word, balloon pods? So if you are running on top of Kubernetes installation that does auto-scaling, if you have policies to auto-scale your cluster, and you want the cluster to auto-scale both in your workload. So you have a horizontal pod autoscaler, your pods will auto-scale, but then you have a cluster autoscaler configured that will auto-scale the cluster itself to fit those pods. You know, one of the biggest challenges is that typically provisioning nodes take time. So your deployment might auto-scale, but then your pods will be pending while the infrastructure auto-scales, right? So a typical, very hacky way of avoiding this is running lower priority pods to keep nodes running, so that when higher priority pods have to autoscale, the low priority pods will be killed and the high priority pods will be scheduled. DRA kind of follows the same philosophy, which is if you have a job that requires GPUs or TPUs, and then you have pods which are already running that have GPUs attached to them, but they're not utilizing them, so it looks at the metrics, the utilization metrics of the actual GPUs, Kubernetes can unschedule those to schedule the things that need actually accelerators, right? The last one is something called in-place VPA. So VPA stands for vertical pod autoscaling. So instead of autoscaling horizontally by adding more pods, you just resize existing pods. In Kubernetes 1.27, a new feature was added where you could actually live resize pods. So you could just add more resources, increase the amount of memory and CPU a pod have, and then vertical pod autoscaler have been modified to take advantage of this feature where it can autoscale a pod vertically by adding CPU and memory without killing it. Before, VPA had to kill a pod because there was no way to like live resize a pod. But now with this feature, you can actually live resize a pod without killing it. So you can look at those later. That's all I have for you. I hope it was useful. I would be appreciative if you can give me some feedback. This is the form that the team sent me. So feel free to scan the QR code, or if you find somebody with the purple T-shirt, tell them I sucked at doing this talk. And yeah, with that, thank you very much.